Just before the break, we were looking at the column design. And what you get from the interaction diagram is only one, couple of things actually. For now, it's the reinforcement ratio, which is the 1%. Then because we know the reinforcement ratio, and by definition, what is reinforcement ratio? It is the area of steel divided by the gross area. That's for column. So we multiply the 1% times the column dimensions, which is the gross area. And then what you get here is you get 3,750. I need to remind you, if this column is circular column, then if circular column, so the area gross is by multiplied by the diameter square divided by 4. Please don't forget that, huh? The area of the circle is by multiplied by the diameter square divided by 4. Then this is the area, and I need to see how many bars, and I ask you in the beginning to use 20 m, so we know that every 20 m is 300, so hopefully everyone knows this number by now. If not, there is a table that you can extract this number, and it's not very difficult. If you divide the 3,750 by the 300, you get 12.5, and you know 12.5 doesn't work. So for sure, there's nothing called 0.5. So you go to 13, and 13 also doesn't work because the column must be symmetric. So we will go finally to 14 bars because 13 doesn't work. So 14 bars times your the area of a single bar, that's 4,200 millimeters square. And so now, please, try to understand that what you see here is a final product. It is not work in progress. Really, what you start in the beginning by this, you have a box, and this box, we know the dimension, it is 300 by 1250, and we know that there will be a 14 bars will go into the column. So 14, if we add here on this side 3, and we have on this side 3, that's 6 from the 14. So then we have 8 left. So the 8, we add 4 on each side. So here we go with the 14. Now, really, the problem, this is something we will figure it out soon. So this configuration of the tie, we will figure it out soon. Okay, so at this point of time, we have a rectangle, and this rectangle has 14 bars, 3 on this face, 3 on this face, and then 4 on this face and 4 on this face. That's what we have right now. I will show you in a minute how we create the tie geometry. For sure, this one is easy. The exterior tie is always required. The exterior tie is always required. But the question is, do I need those like 1 and 2 other ties? This is what I'm going to teach you in a minute. Now, there are a few checks you have to ensure, and I know that this part is not easy. It's kind of tricky because there are so many conditions that have to happen on the same time. Number one, we need to make sure that there is enough spacing between the rebar, which is here. So what I did here, this is what should be the minimum spacing. So as usual, it is 1.4 the bar diameter and 1.4 aggregate size, or at least 30 millimeter, which means 30 millimeter governs. It means in between the rebar in any direction, you need to have a 30 millimeter. And so what I did here is I found the X1 and X2. So what's X1? It's the distance between, clear distance in between the rebar on this direction, and X2 is the clear distance between the rebar in this direction. Not super science. Please watch this. It is a 300 mil minus 2 cover minus 2 tie minus 3 bars. This X1. Count with me. 1, 2, 3 bars. So that's 3 times 20. And then finally, we divide by 2 because simply we have 2 spacing. So that's X1. Happens to be 70 millimeter. More than 30, great. X2 is 1250 minus cover and cover, so to cover, tie and tie, so 2 times 10, and then we have 6 bars, 1, 2, 3, 4, 5, 6, so minus 6 times 20, and then whatever you get, you divide by 5. Why? Because we have 1, 2, 3, 4, 5 spacing. Remember, The spacing is always the number of bars minus 1. So we know that the spacing x2 is 206. It means both of them, they exceeds the minimum spacing. Okay? And you can tell also what I did here, very simple, just like beams. We want to make sure that you know the cover, sorry, that this dimension can accommodate 320 m bars, which is by the way the same. Once you estimate your x and happens to be more than x1, one happens to be more than 30 millimeter, it means you can accommodate. I mean, those are equivalent. So if this is more than 30, it means this is happening already. Okay. Also in the code has a condition that the distance between the rebar maximum 500 mil. That in the code says the maximum spacing between the rebar is 500 mil. And since x1 and x2, both of them, they are less than 5 mil, so this condition is also accepted. I mean, let me ask you, can I have here a bar on this corner and a bar on this corner? Can I do that? That's it? I don't think so. Why? Because this is 1250, and if you estimate the clear distance, it will be more than 500. Remember, if it's more than 500, what you have to do, you must enforce it, which means you have to add more bars here on the side, so you end up with a distance less than 500. And that's why, by the way, so you know, when I designed this problem here, initially I asked for 25 mil, like 25 m. So this here, initially it was 25 m. Here. Oh my God. So this number here, initially, I designed it for 25 m, but then I figured out 25 will not work. Okay, and I will tell you how. Let me ask you guys, if the area required here is 3750, how many 25 m? Any help?
So that's, you divide it by 300.
No, the 25 m each bar is not 300. The 25 m, the cross section area
700,
is
700.
no, not 500. It's 500.
Oh yeah, 500, yeah.
The 30 m is 700.
Oh
Okay,
yeah.
and if
So
you divide this number by 500, you end up with 8. 8 and 8. It means what? It means 4 on the corner. It means 4 on the corner. Okay, and simply also what you get is 2 here and then 2 on this side. Okay, and so what happens here, this distance, uh you can, I'm not sure, we can check right now, but probably it's going to work as well. Probably I was not really thinking deeply, because really if you measure the distance, I mean you estimate the distance from here to there, and it happens to be less than 500, it means we don't have to add extra bars. But if it happens to be more than 500, it doesn't work. We have to add more bars. Anyway, I'm going to be consistent. I will just live with the 20 m. So this is 20 m. So anyway, so right now, really, my thing is, I know that my concrete dimension is 300 by 1250. I have 1420 m, and let's go and discuss what should be the shape of the stirrup. Oh, sorry, the tie, the shape of the tie. The question is, do I need like those extra ties in the middle? Like the one on the exterior, for sure you must provide. There is no other option. You must provide this exterior tie that wraps around everything. But the question is, do I need those? As I said, when what you see is the final product. I'm going to convince you, yes, we need all of those. But it doesn't mean that in an exam, you just have to wrap around every 2 bars or 4 bars. That sometimes is not required. It depends on some calculation. So really what I did here is I'm going to show you right now how to do that. This is very important. I want you to bring your attention. This is very important and it's tricky. So please pay attention. So the way we figure out the geometry of our tie is we inspect every single bar by bar. We inspect every bar in the column bar by bar. And how we do it, we ask ourselves, Is this bar okay or not okay? Let me ask you one question. Guys, remember that always we provide the exterior tie. With the exterior tie, this bar here is okay or not okay? This corner bar is okay or not okay?
That's okay. It's always there.
This bar is not always there. This bar is always confined and restrained by the core by the tie, because it doesn't go in the X or in the Y. Because the tie, you can tell, look at the shape of the tie, it cannot go anywhere. Okay, it cannot go to the outside. I'm gonna point out. So this guy is wanting to go outside this way. It cannot, because of this exterior tie. And similarly, exactly the situation for all the corner bars. So the exterior tie will make all the corner bars, and we have 4 of them, okay. So we don't have to question them. Huh? Those bars, we don't have to question them. They are okay. Now let me ask you, how about this guy here? Is okay or not okay? Which is, by the way, same condition as the same one on the other side. This bar in the middle along the 300. Is it
It's
okay?
okay because without it, it's more than 150.
Exactly, Gord. What you have to do is you have to estimate the x1. And I think we did already found x1. So as long as x1 is less than 150, it means, you know what, the tie is so short and it can confine and restrain this bar from going outside. The problem is, think about it as a beam. So think about the tie as a beam that spans between those 2 corner bars. The longer the beam, it means it is weaker and it cannot confine this bar. And here we go. We solve this bar and this bar over there. If this distance is more than x1 is more than 150, it means no. It means this bar must get its own restraint. Okay. Now, let's go ahead and do another one. Here we go. So let's do that. How about this one? Okay. So when you check this one, you will find, again, remember that this tie here and this tie here does not exist at the moment. This is my final finding that I need them. But I'm asking you, think about it, please. I know this is maybe shortcoming on my end. Probably I should have prepared so many steps, like sequential, like step 1, step 2, step 3. But it's very, very rushing. I prepared this one immediately before the class. Okay. So please imagine at this point, interior ties are not available right now. We need to know whether we need them or we don't need them. So now I have one bar in question, and those are not don't exist. Do I need them? Guess what? Look at this. So this tie or the distance from this guy in question to this bar is way more than 150 mil. Yes, from one side, even from this side, even it's 206. Okay, so obviously this guy here needs some restraint. And please, when you do that, do it sequentially. Like, don't question all of them at the same point. You have to question one bar at a time, because simply when you fix one bar problem, maybe sometimes it fixes the other bar problem. So do it one bar at a time. And so when you think about it, because this x2 from this dimension from here to the nearest, to the farthest restrained guy is way more than 150, it means no, we need to provide a lateral support for this bar. How? So simply, we have to provide this tie. And what happened is, once we provide this tie, it solves already same problem of this guy and this guy and this guy. Now let's move on and see. We have those four in the middle. We need to know whether they need support or does need support. One more time, let's look at the dimension. So from, let's say now my question is, I'm asking myself, do I need a restraint for this guy here? Let's do it. So what you do is, you check from this guy in question to the farthest restrained one. Is that more than 250? Yes, it is, which means it needs some tie. Okay, so I just had to provide this last tie here. So please understand that this is not always the case. If I shrink the 1250 a little bit, what you will end up is, you will end up sometimes we don't have to restrain all of them. I have a document which I think I will need to upload to the not yet upload to the O drive or to the D2L. Watch this, please. So watch this, please, for example. Okay. I have one example here where I'm trying to see what is the shape of the tie. So the column is 300 by 700, and it has those 5, let's say 20 M bars. And adding one tie at the very exterior tie, yes, it resolves the problem of this bar and this bar and this bar and this bar. However, it doesn't really resolve because this is too long and simply those bars come buckle to the outside. What I'm trying to tell you is sometimes when I add this tie here, it simply resolve the problem of this guy. Why? Because all you have to do is you need to measure the clear distance from this guy to the nearest supported column. So if the thing is, if this is less than 150 mil, it means we're okay. It means supporting this this bar here, it means it solved the problem for the bar itself and also solved the problem with this bar and this bar and this bar and this bar. Hopefully this is clear. I know some of you got it, and some in the exam, what they do is, I know what they do. They always wrap, either give me the one exterior one only, or they wrap around everything. So anytime they see a bar, what they do is they wrap around the bar. For example, look at this. Okay, so if I can do that, it means this guy can resolve this guy. I tell you in the exam, I'll show you what people they do. They do this. They come back and they do here a tie as well here. Okay. So that's why in the exam, if you give me the exterior tie, no mark. If you give me a tie around everything and it's not required, also it's no mark, because that's something you've done without any thinking. Okay. So anyway, here. Now, the next part is very simple. We need to think about what is the bar tie diameter. We said it's 30% of the vertical bar, and so this is 6 millimeter, and we have no 6 millimeters, so we use 10 M. And then we talk about the spacing between the rebar, which is you have to estimate 3 numbers: 16 times bar diameter, 320, or 40 times the tie diameter, so this is 480, or the least column dimension, which is 300. Obviously, the least of them is 300. And remember, this one is not applicable because we don't have bundled bars. So finally, my ties are 10 M at 300 millimeter on center. And my column, it has 420 M vertical bars. And my column is 300 by 1250. And then finally, you want to find the splice length. The splice length. How do we do that? Let me remind you. So I have to go back to my interaction diagram, and here is the point. And you can tell my point is happening more than Fs divided by F field, more than 0.5. Remember, this is compression only, and this one is splice A, and this area is a splice P. And let me ask you, is that splice A or splice P or compression? Any help?
Splice B.
Splice B, and it means this column has lots of eccentricity, and simply it works like most like a beam. And so what happens here? Nothing super here. You go to your table, and this you're gonna use this chunk of the table, class B, and then you go with the F prime C30. You go with the 20 M, and finally you need a splice length of 680 mil, and that's what you have to provide between the bars projected from the previous column to the bars to the next column. Okay. Are you following so far?
Yes, sir.
Okay,
Yep.
so I will add to that something I'm pretty sure that you know about it from other course, but I will do it no matter what. It's about live load reduction. Did you hear about live load reduction in a steel course?
Can't
Hello.
remember. Can't remember.
I don't think yet.
Okay, so I said I'll do it. I'll do it no matter what. So here is the point. Live load reduction. It is something. So this page here you see on my screen is coming from the National Building Code, from the NBC. It was the same over the years, no change from 2005, 2010, 2015. It is always the same. And I'll tell you the idea. So the idea, let's say this is a high-rise building. So I'm gonna draw for you a column in a high-rise building. Okay, so that's the roof, and those are few floors. So that's the floor. What you see here is kind of elevation of the high-rise building. Okay. Another one here. So let me ask you, this column here, it does support what? What does it support? Looks like this column will support this floor and 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 the roof, correct?
Correct.
Yes.
Now the question is, when we try to find the load on this column here, as I said, it supports floors plus the roof. I'm asking you, what is the possibility that the live load is acting in full in all the floors at the same time? All the floors on the same time, we have a full live load. It's a slim chance, slim probability, and that's why the code allows you to change or reduce the live load. Remember, I want to make it clear, 100% clear. This whole discussion doesn't talk about dead load, does not refer to snow load. It refers to only one load called live load. So anything I'm going to say right now, it doesn't apply for dead, it doesn't apply for snow, it applies only for live load. And it's a reduction. It means we can reduce live load. And I know some of you will say, oh my God, Tahir, we are week 13. Week 13, okay? And you're talking right now in week number 13 about live load reduction. Why you haven't said a single word about live load reduction from day number 1? Anybody have the same question?
No, we have faith in you, Tahir.
Okay, I'll take it. Okay, so the thing is, live load reduction is a concept applies to all structural member, beams, slabs, columns, footing, any structural member. We can definitely reduce the live load acting on this member. But the thing is, it is function of the tributary area of the element. Beams and slabs a very small trip width or trip area. And that's why even if you want to apply, the live load reduction will be 1. It means no reduction. You will see this shortly in the math. So for example, let me show you. So this equation here doesn't matter for now. Let's take any of them. So the code has different equations for different cases. But let's take this one here, 0.3 plus square root of 9.8 over b. Okay, let's take an area, a trip area of 20 meters. So this B here is the trip area of your element. Remember, the element can be anything, can be a beam, can be a column, can be a footing. Okay, so this trip area of the live load. What is the area covered by the live load? Now I need some help. Somebody to go ahead and find for me 0.3 plus square root of 9.8 over 20.
So we got 1.
1. And what does it mean 1 in math? If we multiply 1 by anything, what do we get?
Any value that is multiplied by 1 is the value.
Okay, so no reduction, but let's go ahead and please, I need some help. Somebody to re-estimate the number for me if we change trip area into 30.
.87.
0.87. And what does it mean? It means, look at it, number is getting less than 1. It means we're starting to reduce. So that's the answer right now. So that live load reduction concept, it's applicable on any structure element, beams, columns, slab, footing, anything. And it applies only for live load. The thing why we haven't even touched this before, because beams and slab, their trip width is very small. However, look at this column. So if I have a beam here, I'm going to show you, if I have a beam here, okay, a beam here on this floor, what exactly this beam is supporting? Is it supporting all the floors or the load only from this floor?
It's supporting all the load from the top.
This beam is supporting all the load from the top. So if I stand here, Tahir is standing here and it's gonna go crazy now, huh?
No. That's not what I mean. It's like it support only in that it support only into that level.
Okay, great. Thank
into
you so
that
much.
level, but it's also the one that is on top of it is also considering that load.
Jenny,
Okay.
if the person is standing here, like this guy here right now, okay? So the load of this guy will go into this beam. But this guy, the load will go into another beam, like another beam here, and this beam will end up supported on this column. But this beam will not see the load of this guy here.
Okay.
Okay?
Yeah.
So I mean, let me give you numbers. Let's say the live load area here, let's say is 40 meters square. Okay, and let's say it is typical. It is typical. It means every floor the live load is coming from every floor is a 40 meters square, like 40 here, and let's copy this one several times. So 40 here. Okay. So the number you see on my screen is the live load area exposed to the live load in every floor. Let me ask you, this column here, what is the trip area of this column? How much?
It's 2 times of that 1/2 times the length of
No. I already gave you the number. So the trip area of the column from every floor is 40 meters square. I'm asking
okay.
you, this column here, what is the trip area of this column for the
It's
live load?
only
Remember, I have
40.
to listen. Let me finish. So I have to be very specific. The whole discussion is about live load. Yes, this column, it supports the roof. Okay, supports the roof, but the roof will have a snow. So let me ask you, this column here, what is the trip area of this column?
Yeah, that's only 40 meters squared.
40. Okay, so how about the column in the basement here?
It's the same, 40 meters squared.
No, this column is supports 40 and 40 and 40 and 40 and 40. So which means we have 5 40s, which means the trip area of this guy is 200 meters square. Hello.
Why is that? Because
the column is
if you're only considering that part over there, so if you're asking for the tributary area, so it only attaches the second level, so you only got 40 meters squared.
so which means this guy here, how can we support this part of the building? Okay, so this part here, so this guy will say, you know what, I will only support this 40. Okay, how about the load coming here will go where? Anyway, the trip area of the column in the basement, the last column at the bottom, for sure it's the sum of all the trip area of those trip area of all the floors. So the trip area here is 200. This guy, the trip area here is 200 meters square. Okay. So anyway, so I'm gonna show you right now. So that's an elevation. I remember what you see here is an elevation, not a plan view. This is elevation. How about the plan view? So now Jelly is how we estimate the area. Those 40, how do we estimate the 40? I think you were about to go this direction. This is how you estimate the area or the trip area of every column. Okay, so in this plan view here, I showed you different columns. So I have here a central column, like in blue. So very simple. You just have to go to the next column in each direction and take halfway. So here is one column, and here is another column. So this line here is halfway. and you do that from all direction, and the blue area is the trip area of this column. Remember, you have to think about how many floors is that column in under the roof or in the basement, because simply you multiply the blue by how many floors supported by this column. Now, if you have an edge column, which is like the green, this guy here, same thing, there is no slab here, so you go halfway to the next column from all dimension, and the green area is the trip area of the edge column. How about the corner in yellow? Same thing, there is no slab on this side, so you only go on this direction, take half between grid line 1 and 2, take half between grid line A and B, and this will give you the trip area of the column from this floor, okay? And then finally, sometimes we have irregular, so irregular, just like the red column. Here there is no slab, so that's an opening. So this area here will be taken out of the business, and the area in red is your trip area from that floor, okay? Now, let's go and look at this one more time in more details. So the code here, I don't want to take you deep into this discussion. I want to go on a very high level because we have no time for that. So the code here gives you a reduction factor, a number which it could be less than 1, which you have to multiply by the live load only, and I will say it 100 times. The dead load is out of the business, the snow load is out of the business. So let's say if we get here 87%, we multiply live load by 87%. We don't touch the snow, and so the snow load doesn't change or dead load doesn't change. The one in this discussion is only live load. Why there is so much discussion? Because simply it depends on the occupancy. So if you give it a read, for example, I will only read number 3. So number 3, I will, for the sake of time, I will read only number 3, where a structural member supports a trip area of a floor or roof or combination that is greater than 20 square meter and used for any occupancy other than those indicated in sentence 1 and 2, then the reduction factor will be 0.3 square root of 9.8 divided by the B. Let's go ahead and let's say read number 2 as well. Where the structural member supports a trip area of floor or roof or combination that is greater than 80 square meter square and either used for assembly occupancy, designated for live load of 4.8, or sorry, designed for live load 4.8 or more, or used for storage, manufacturing facility, retail store, garage, food bridges, those we use the 0.5 plus square root. I don't want to be distracted by the equation. It's as simple as if the condition on statement number 2 is happening, then we use 0.5 plus a square root of 20 over A. If they are not happening, then we go to statement number 3, where we use a different reduction. At the end of the day, those are reduction factor, so there will be maximum 1 or 0.9 or 0.6 or 0.7. It depends on the trip area. And the trip area changes, by the way, it's not the same. So if you have a column on the roof all the way to the down to the basement, every section of the column, the reduction factor will change, depends on how many floors it supports and what's the trip area it supports. Okay. Now there is a example coming from the code just to illustrate about the live load reduction. Okay. So this is coming from the code, and as I said, I'm not going to dive deep into it. I'm going to solve the assignment, which has a little bit of reduction, live load reduction. So you want to hear here, and also you want to look at the assignment as well. Okay. So I would say here the bottom line is every floor drops at 27 meters square from every floor. So every floor delivers 27 meters square new to the column. Okay. And so there are some other input here which I don't want to distract you, like it gives you the column, like the column dimension, it gives you the beam dimension, and this adds up to the dead load of the column and the beam. I would say that's not really very important. Really what's important is you can tell here there is estimation of dead load, which includes the sill weight of the slab, the beams, and the columns. Everything ends up with 28. It means every column, I'm sorry, sorry, that's the roof. So this number here, 217, this is the dead load from the roof. Dead load from the typical floor is 254. And then the snow load from the roof is 65. Okay. Now, how do we solve this problem is we do it in a table. And please think about it same as the profile I had before. So this is my roof is here. My roof is here. And my column is going all the way down to here. And every floor down, I'm adding more load into my column. Okay, so I'm going to draw some lines here, and those lines are simply every floor. The fifth floor, the fourth floor. Okay. Now, what happened is here, all really I want you to show you is there is a separation. You can see here, those numbers are only dead load. Those numbers are dead load, and nobody is going to touch dead load. Dead load will stay the same. Okay. How about the live load? So the live load here, this is the trip area. This number here, those are the trip area. And if you notice the trip area, we at this level here, we get 27. So at this level here, we got 27 meters square. How about this level here? We got another 27, and you can tell 27 and this column 54, and then we add more 27, 81, 108, 135, 162, and 189. And because the trip area is changing, what we have to do is we also have to change the reduction factor. Remember, the reduction factor is 0.3 plus 0.3 plus square root of 9.8 divided by the B, which is the trip area. So really what you have to do is you have to estimate the reduction factor for every section of the column. Based on what? Remember, we don't care really what's the value of the snow or the dead. We don't care. This will stay the same. What we have to do is we need to take the trip area of every section of the column, use it here, and this will give you the reduction factor for every part of the column. You guys can do that right now probably once or so. I need some help. Can somebody use the 189? And what is 189? Simply, it is 1, 2, 3, 4, 5, 6, and 7 times 27. 7 times 27, what you will get is 189, because this section of the column simply carries seven floors. 7 floors. And why not 8? Why the roof? Because it is about trip area of the live load. So the area of the roof is not included in this equation. It is the trip area of the live load because it's a live load reduction. I need some help, please. I need somebody to use this equation to find for me what should be the reduction of the live load if the trip area is 189.
0.52771.
Which is 0.58 here. So listen what's happening next. So I'm asking you the live load, okay? I think the live load requirement, let's see the live load requirement here. The live load requirement is, can anybody see what is the live load requirement?
Is that 3.6? No. No.
This is floor to floor height.
Yeah,
I think I can get it here.
no.
Actually, it is 2.4. So actually, it's live load 2.4. So that's the live load requirement 2.4, and it's office building. So okay, so let me show you. So if you multiply 2.4 times 27, 2.4 times 27, what do we get?
64.8.
Okay, you can see it's here, huh? So this is 64.8, which is roughly 65. But the question is, do we use 65 or we reduce it by this amount? We reduce it. So we don't really, so this number here, it's the actual live load without reduction. So those numbers here, those are the live load on the column without any reduction. We're not using those. We have to multiply this column times this column. So we take the 65 times 0.902, and simply you can see this is my final reduced live load. Okay. Also, what you have to do is you multiply your 455, which is the live load on the last section of the column, multiply it by 0.528, because simply this is the reduction of the live load. Remember, we're not multiplying 0.528 times dead or times snow. We're not touching those. Don't touch those, huh? Those, don't touch them, because the live load is reduction factor for live load only. So we multiply this column here, which is the live load, you multiply by the reduction or the reduction factor, so you get finally a reduced live load. And then what's next? Then you go into the load combination. Remember, load combination is we do load combination number 1, we multiply 1.4 times D, so we take 217, which is dead load, you multiply times 1.4. So you will get this number here, which is, remember the numbers are in meganewton. So if you multiply this by 1,000, you'll get 300. So 217 times 1.4, you will get 300 kilonewton. Okay. And then load combination number 2, it is 1.25 D plus 1.5 the L. Remember the L here, this L here, it is not the 65, it is the 59. So we simply, after we reduce them, this is gone. We don't use this one anymore. Okay, we cross this one. What do we do is we choose this one here. This one is the correct one that it carries on your load combination. This concept is difficult. Live load reduction. It's as
Not
simple
bad.
as, excuse me?
That's cake.
Very, very simple. Again, this one I know it's kind of complicated because we have so many floor. I'm going to show you in the assignment model answer. How do we do that in the assignment? I have only one roof and one floor, and probably it will be easier to follow me in the assignment model answer. Okay, now, anyone have any question before we say goodbye and see you sometime on Wednesday?
No questions from me.
Okay, so thank you so much for attending. I want to see you guys on Wednesday morning. Harjut, I think.
Hi, Tahir.
Hi, how are you?
Fine. I have a question about rebar layout. On the slide number 12, how we know like we gonna put 3 rebars vertically and the remaining 5 rebars horizontally, because I calculated and we can still put 4 rebars vertically and we will still maintain minimum spacing of like 30 mm.
To be honest, this question is a really nice question. You know, typically when you say it's like the code says uniform, and the way we split, so the Harjut question is, why do we add here 3 and here 3? Why don't we add here 4? And so if we add here 4, then we take one of those, so we left with 3 on this side and 3 on this side. I would say typically we go by the ratio of the length. So if you divide this 300 divided by the perimeter of the whole column, then it will tell you how many it should have on this column side. Like for example, if you go ahead and say 300 divided by, we have a 600 plus, so that's 310, huh? So what you see 3100, that's the perimeter of the whole column. And then if you multiply this times 14, probably this will tell you how many do we need to have on this side. Okay. The thing is, we are adding bars uniform around all sides of your column. Okay, so thank you so much, and please, everyone leaves, and I need to talk to Nick. I need you to talk to Nick.
Thanks, Tahir.
Okay, thank you so much. Have a good day.
You too.